Cool, thanks for having me today. I'm going to be talking about when does uncertainty matter while modeling climate change in mountain headwaters. And more specifically, I'm going to be talking about looking at model resolution and how that relates to complexity in an alpine catchment. I've put change in brackets here for those of you who don't believe in climate change. I just wanted you to feel more comfortable that we could frame this just as climate, if you so choose. So right here in red, I've outlined the actual basin I'm going to be talking about. This is the East River catchment in Crested Butte, Colorado. If you ski, in the top left of that mountain is actually Mount Crested Butte. And so you can get a sense of the scale. It would take a long day, but you could hike the whole catchment. It's probably about 12 miles long, and it's 255 square kilometers. So I'm going to spend most of my talk talking about the background and parameter scaling, which is a paper that's in review right now. And if you're interested, I'm going to briefly cover the second paper I'm working on, but there's also a poster on that if you want to learn more. So most people in this room know that as temperatures increase, we have less snow. But you may not know that all those regions on the globe with red outlines are populations that depend on snowmelt-dominated systems primarily for their water supply. I think I'm sneaking away from this. Sorry. Okay. So the other thing is the blue on this graph is showing regions of topographic complexity, which is something I'm going to be talking a lot about today as well. And all of these regions amount to about 1/6 of the world's population. And so bringing this more locally to what I'm going to be talking about, this is the Colorado River Basin in the United States, and this star is where the East River is located. So streamflow from basins like the East River provides 85% of the upper Colorado River streamflow, making it a critical region to understand. That being said, mountains are likely to warm more quickly, so they're more sensitive to climate change. And this has been in the literature for a long time, but just in 2017, there was a review article that basically established scientific consensus around that fact. So we know mountains are sensitive, but they're very, very complicated to model or observe. And so this is, again, the East River. This is now the model of the East River, and I've highlighted the watershed again in red. And you can see that we cover almost 1,500 meters of elevation just in this 255 square kilometer domain. And what that means is we have really steep temperature gradients everywhere, and we have variable precipitation. It could be raining right here where I'm standing and not raining over there on the other end of the room. If any of you have hiked in the mountains, you may have experienced that yourselves. And because of that, these systems are really difficult to model. That's compounded by the fact that our geology is incredibly complicated, and so is our land cover. And so the question here is, how do we learn about these systems if they're so important to our water supplies? And all of our methodologies are going to simplify the real world to some extent. So we can have local point observations, and those are going to give us high resolution in time, but they're difficult to scale in space. And as you saw, these mountain systems are very heterogeneous in space. Now we can have remote sensing, which is going to give a combination of space and time, but this GRACE satellite shown in this image, which you may remember from the science cover showing California drying out during the drought, that was observations made by this satellite, that each pixel of that satellite is 300 kilometers, which means that that's not going to be incredibly useful for us if we're looking at those tiny mountain headwater basins. And then we can also do flyovers and get high resolution in space, but there you're limited in time. So from a modeling perspective, we can use coarse resolution and simple algorithmic models to predict our water supply, and most operational models do use a combination of this. And those are useful because they run quickly, or they can cover a large area of the globe like a global climate model, but not high resolution in local regions. And when you don't get those high resolutions in the headwater basins, you're missing those feedbacks driven by those steep temperature gradients. So this is a table of most of the studies predicting Colorado future stream flow since 2013. And there's a lot of information on there, but I'll just highlight the highest resolution study on this entire list, which is at 2-kilometer resolution. And so that's like the maximum resolution being used to predict our stream flow. Now we could increase the resolution of those models, but then we're limited by computational demand, and a high resolution model would not be useful for making operational decisions. So the real question is we have all these different methodologies and we want to figure out when it matters to get which pieces of information. And that's where HPC systems can come in and help us fill this gap. Using high resolution enabled by parallelism, we can actually bridge the gap in observations and in models. So this is a paper that came out recently in the hydrologic community that was pushing for more hyper-resolution models. A hyper-resolution model is going to allow us to get high resolution in both space and time and start to link point observations and remote sensing observations. It'll also give us some insight into the physical mechanisms driving changes instead of just understanding total volumes. And finally, it can help inform our decision and predictive models, since these HPC models can never replace those operational models, at least not with the current computational constraints. So we use a model called ParFlow-CLM. And as opposed to matching a signal with an algorithm, ParFlow-CLM attempts to solve as many underlying physical processes as possible. And so what we do is calculate pressure at every location in the domain, which means that surface water and groundwater can interact at any time and in any location dynamically, instead of being in separate models that are then coupled together. Our land surface model includes a 5-layer snow model, evaporation, transpiration, and a full energy balance. And what we give the model as input is weather data. From a computing standpoint, what that means is that it's a multi-physics, PDE-based system where we solve the nonlinear diffusion and wave equations globally, implicitly, and in parallel. So we take that model and we build versions of it for this East River domain that I mentioned at the beginning of my talk. And I have versions of this model at 1 kilometer, 100 meters, and there's actually a version at 10 meters that I'm not going to discuss today, but I'm happy to discuss with you afterwards if you're interested. And what you'll notice, just looking closely at the 100 meter and 1 kilometer versions, is that you start to lose a lot of information as you decimate up to 1 kilometer, which you'll remember is pushing the limit of the scale at which we're predicting future stream flow. So even though we have very small difference in the amount of certain types of geologies or certain types of land covers, and therefore in the amount of certain parameters, we actually get very different streamflow estimates. So here, I'm bringing up the original baseline parameters for the 1 kilometer and 100 meter model. And remember, these are very, very similar models. And the purple line is our 1 kilometer model, and the green line is our 100 meter model. And you can see that those streamflow estimates are vastly different with the same parameters. And so we needed to understand why this was happening. So for those of you who aren't hydrologists, I'm going to explain the most important parameter for estimating flow, which is hydraulic conductivity. And if you remember your intro physics class, electrical conductivity is an inherent property of certain substances, and it represents how conducive a certain material is to electrical flow. And hydraulic conductivity is almost exactly the same as that for groundwater. All groundwater has pore space, and, the ground underneath us is filled with tiny pores, and some of that ground is saturated with water. And so each different geology has an inherent property about it that says how quickly water can move through certain geologies. So the first thing we did was do a large sensitivity experiment covering 4 orders of magnitude of hydraulic conductivity in 3 different subsurface layers. And so I'm going to start by explaining hydraulic conductivity's role in determining flow. So I'm plotting a hydrograph here, which means I'm starting in October and going to October 2006. So this is 1 year of data, and you can see the base flow period is when the snowpack is building up and temperatures are cold and our rivers aren't flowing too much. And then in April, the snow melts and we get this giant peak flow event. And then in the summer, in the mountains, we have these monsoon seasons with heavy rains, which you might think of as being the instigators of flash floods in Utah and the Colorado Plateau. And so that's why you see those sort of quick events. Now, hydraulic conductivity, which is again the subsurface, the resistance, or actually the ease of subsurface flow, is a moderator between our change in storage and our output. And you can see that as hydraulic conductivity increases, which means that we have easier flow, we see more dynamic subsurface movement and less dynamic stream flow. But the other thing you'll notice about this is that high K case looks a lot like our streamflow in the 100 meter model, and that low K case looks a lot like the streamflow in the 1 kilometer model, even though they're modeled with almost the same geologies, and that's how we defined hydraulic conductivity. That's how most people would in a modeling case. So what causes the resolutions to cause different flow? So I'm going to start with a really simple model of hydrology, which is that water flows downhill due to gravity and is resisted by friction, which is 1 over hydraulic conductivity. And if we take our hypothetical mountain and we divide it into boxes, what we do is we lower the slope term of our gradient. And so we're reducing gravity when we go to coarser and coarser resolution models. And keep hydraulic conductivity the same, because it's defined by geology, then all of a sudden we're changing our flow. So here's the actual model, and you can see that same effect in the model. I'm just plotting the elevation right there. So what we propose to do with this new method is to combine the uncertainty in hydraulic conductivity with the loss of gradient from coarsening resolution into a term we're going to call effective K. So instead of thinking about that parameter as inherent to certain geologies, we're going to think about it as inherent to certain geologies at certain scales. And that's a concept that's very common in the observational literature but has not been applied to modeling. So up at the top, I'm showing the range of variation for crystalline, which is the most prevalent geology in my basin, and you can see that it ranges over 11 orders of magnitude. And so it's a very uncertain parameter, and it makes sense to combine other uncertainties in our model into that same parameter. So what we'll do is mathematically define K effective instead of K, and the nice thing about this is that it's consistent with the underlying mathematics. So as our model at some resolution approaches the real system, sine theta will go to 1, and our effective K will approach actual hydraulic conductivity for certain geologies. And so what we do is, here I'm plotting the domain, and you can see 1 kilometer on the left, then 100 meters. And in the top row, I'm plotting the actual hydraulic conductivity based on the underlying geology. And you can see they're not very different from each other. But in the bottom row, I'm plotting that if we calculate the effective hydraulic conductivity instead. And you can see that they are quite different. So we would want to minimize this difference in order to fix our streamflow. So what we're going to do is take the ratio of effective K at 1 kilometer and 100 meter resolution, and that's shown on the left. And then what I'm going to do is minimize that ratio with a constant value, and that's shown on the right. And I'm going to multiply that constant value by every 100-meter hydraulic conductivity value. That way, I'm minimizing the difference in our effective K values. And what you can see happens is that we get a dramatic improvement in our streamflow. So now the purple line is still the 1 kilometer model, the green line is our new 100 meter model, and the dotted line is the 100 meter model before applying this method to scale hydraulic conductivity. So the reason this would be so important is that we can parameterize hyper-resolution models where a traditional calibration method would be infeasible. So for example, with this example, we make a simple version of our hyper-resolution model. And then it runs quick enough that we can actually tune the parameters and get them where we need them to be to match the observed streamflow signal. Then we apply our parameter scaling method, and now we have an accurate fine or even up to hyperscale model on which to test our experiments. So this is opening the door for better hyper-resolution models. So to move on to the next study, which again I'm just going to go over briefly, we now have these working 1 kilometer and 100 meter models with good parameters, and now we can start to look at the uncertainty in resolution versus climate change impacts. So global climate models, as I mentioned, and regional hydrologic models are known to perform poorly in the Rockies. This graph on the left shows a bunch of different downscaling methods from climate models on Pacific Northwest rivers, and you can see that those streamflow estimates are incredibly variable from those different methodologies. And so this begs the question, are our models more uncertain than the climate impact? Because if they are, then we might not be preparing for climate impacts. We might not be detecting an actual climate signal that's useful. So what we wanted to do was compare climate variability with the variation in modeling resolution. And so I ran 30 different climate scenarios from projections for the Rocky Mountains. And the way I'm going to plot them is just, I'm going to plot temperature as different lines. And then since I ran 12 different precipitation cases, I'm just going to plot those as a shaded region for each temperature. And we ran all of those cases on the 1 kilometer and the 100 meter model. And the punchline of these results is, and actually let me explain this graph real quick first. So you can see on the far left, the line for the 100 meter and the 1 kilometer models are both at 100% of their baseline value because that's the baseline case. And then as you go up 2 degrees, they lose stream flow compared to baseline, and up 4 degrees they lose stream flow. And then again, the shaded region represents all of the precipitation cases, again, as compared to baseline. So the first thing you'll notice about that graph is that the slope of the 100-meter line trend is much steeper than the slope of the 1-kilometer trend, which implies that our higher resolution models are predicting greater climate impacts. So that might imply that there's some nonlinear feedbacks going on or something that's driving bigger decreases in stream flow than our coarse resolution models see. And that's a big deal because the models that currently give our water managers information are coarse resolution models. So I can go over that in more detail if you want to come check out my poster. It's over there, and I'm happy to explain or today answer more questions. So why systems like Blue Waters? Obviously, computational demand. These sorts of simulations wouldn't be useful operationally because they demand a lot of hours. These are the hours for each of the different studies that I've presented today, which adds up to 150,000 core hours. And that doesn't really count the experiments that didn't make it into the paper or the many mistakes that happened along the way. So to conclude, hyper-resolution models and HPC systems can help us understand important complex systems like mountains. Model interrogation and development are critical to getting the right answers for the right reasons, i.e. model sensitivity and parameter estimation. And finally, how we build and use our models is as important as the climate changes they are built to detect. So we have to be thoughtful about our results and the models that they come from and then their implications. I want to do a quick thank you to the Blue Waters cohort, my point of contact, Galen, who worked tirelessly on getting ParFlow running on Blue Waters. And then down in the bottom left, I work a lot with Berkeley National Lab and on Cori, which is their supercomputing machine. And so there's many observational scientists who I collaborate with in that East River Basin, which is a focused area for Berkeley. And then on the bottom right is my research group, who are a group of close friends and drinking buddies for when the models don't run. And I love them very much. I'm going to leave you guys with this thought. Again, I have change in brackets because I think sometimes when we inform people about climate changes, we kind of want to beat them over the head with how big a deal it is, but a lot of people are struggling with the level of information that's being shared, and I'm sure all of us have felt this way on a probably near daily basis for the last couple years. And so maybe we could be more gentle about how we communicate that, and we might be more effective.